All right, thank you for the introduction. So I would like to point out that I am one half of the infrared program at the Advanced Light Source, which is a synchrotron user facility. And so I hope to convince you during this talk that coming to the light source as a user is something that's valuable. And even if you decide you don't want to come to the ALS in Berkeley, several of my colleagues are here from our sister facility at at Brookhaven National Lab. So come speak to Larry or Lucas during the poster session for more information about their capabilities. But I'm going to be talking today about nanospectroscopy and nanoimaging, which we do quite a bit of at the ALS. And so the flavor that we do, we call it synchrotron infrared nanospectroscopy, or SINS. That's our acronym, and we thank Marcus for that one. But essentially, it's the same general experimental setup as what you see with the laser-based sources. So we have a synchrotron light source rather than a laser. And so as you can see, even compared to some broadband lasers, the synchrotron is incredibly broadband. And so in this case, we're actually limited by whatever choice of detector and beam splitter combination that we use. So the limiting factor in our case for our spectral bandwidth is our optics and our detector. It's not the light from the source itself. And so I'm going to talk about 3 highlights from user groups that have collaborated with us and hopefully kind of indicate the value that the synchrotron infrared nanospectroscopy brings to these measurements. So I'm focusing on 3 2D materials, and so hopefully it'll be relevant to all of you here today. So the first I'm going to talk about is actually hexagonal boron nitride, which we've heard a lot about already. And so in this case, some nanoimaging was done at the transverse optical phonon frequency in this 2D layer. It's 5 nanometers thick, and it was deposited on SiO2 Si substrate. And during the deposition process, this group was actually interested in creating strain. And so they annealed the sample, which resulted in all these wrinkles. And it's a little bit challenging to see with this projector. In the topography, it's maybe a little bit more clear. But all of this structure that you see is actually a result of wrinkles. And so we noted that at the end of some of these wrinkles, there are some little dark spots, which, again, I apologize that they're not totally clear in this view. They're more obvious in the paper. And it's curious. We're seeing a change in the dielectric value, but it wasn't immediately obvious what was causing that. So these regions were observed to be topographically flat. So these wrinkles form along the armchair directions, but if you look at the AFM scans, this region here where we're having a dark spot, it's actually very, very flat. And the wrinkle has some kind of complex shape. It kind of folds over. It's not really a perfect structure. So what was theorized is that, initially when this material is fabricated, it forms a dome that has a little wrinkle in it. And then after you anneal it and apply heat, this dome essentially collapses. It's energetically unstable, so it relaxes into this configuration. And so the question was at that point, how is the strain field that this collapsed shape generates altering the dielectric response? And so to really understand that, we turn to synchrotron nanospectroscopy. And so in this case, there's a nice little cartoon here that demonstrates anytime you strain a lattice, you're going to change the vibrational modes in the material. And so, it was expected that with compression, this TO phonon mode would blue shift. And, for a particular nanoimaging detection frequency, where an unstrained region would have a relatively bright near-field amplitude or high contrast, at the same imaging frequency, the strained region would be darker. And so that is indeed what was observed as we move through the resonance curve here, getting closer to this TO phonon mode. We do see that the dielectric function is lower in these strained regions. These spots get very dark. And then when we move to the other side of the tuning curve, something interesting happens. It's still a little bit dark there and then some bright spots. And it wasn't immediately obvious at this point if these bright circles are phonon polaritons, if they're just a simple change in the dielectric function, as this plot might suggest, or if it's some combination of both. And so looking at another HBN sample that was just a little bit thicker, so this is 10 nanometers compared to 5 nanometers, this film has less strain in it because of its thickness. And so you can see that, we do see some propagating phonon polaritons that are launched from this wrinkle. And then we also seem to see that this, the width of this varies, not just the phonon polaritons from the wrinkle, but the width of the bright spots is changing as well. So that leads us to think that, they might actually be phonon polaritons being launched because of this change in dielectric value. So examining a little more closely, and once again, it's very hard to see in this image. These white lines are essentially guides to the eye, but over here, it's almost invisible on this projector. But there are standing waves that are present, and we can see that as we change frequency, they also change width, as we'd expect with phonon polaritons, and these bright regions also change width as well. So from this, we're able to determine that, the circular region of a different dielectric value is actually able to partially reflect the phonon polaritons, and this change in optical contrast also follows with this photon frequency, excuse me. So just for comparison, it's much more common than the literature to see a 2D material where you're looking at phonon polaritons at a hard physical edge. And so here's the edge of the HBN, and you can see that these regions of strained material actually follow the same trend of starting out darker and getting brighter, and then the phonon polariton waves becoming present. It follows precisely the same pattern as the material edge. So then we wanted to know, is it possible to quantify the strain field in this small region? It's highly localized, and it obviously can't be that high of a strain given the dimensions and everything that we're talking about. So can we quantify it, and how far does the strain field extend? So we turned to nanospectroscopy with the synchrotron and probed a region moving from a region that it was unstrained into a region where the dielectric value was obviously different. And we do indeed see a shift in the phonon frequency. So as expected, there's a phonon frequency shift. This shift was modeled using first principle calculations, and it was determined that the strain in this region is isotropic and biaxial. And so from the combination of the measured shift and these first principle calculations, we were able to come up with this plot here of strain as a function of radius, and the radius is the distance from the endpoint of the wrinkle. And so there were some kind of back of the envelope geometrical calculations that included elastic estimates of the strain. And so you could see here, there's like the radial estimate of strain, and here is the tangential, and then the effective is essentially a linear combination of the two. And the data fit very nicely with this effective estimate of what the strain would be. And I'll point out that the large deviation that happens as you get below 500 nanometers is really a result of the calculation. So when the calculation was done, it assumed a perfect fold in the HBN. And that also includes infinite strain magnitude and divergent strain energy density at the origin, which is not physical in this case. So the combination of all of these results, it was determined that the minimum strain level detected with nanospectroscopy is 0.01%. Or to put it in terms of the material itself, that's a relative lattice variation of 10 to the minus 4. So this technique is incredibly sensitive for determining very, very small lattice strains. And so, yes, I just like to point out that our technique was able to facilitate this measurement. So the next one, I'm going to move on to a topological material. So bismuth selenide is of great interest because of its potential as a topological insulator. But a lot of the challenges that come in fabricating useful samples in this particular system come from localized defects. So if you get any kind of carrier conduction in these systems, it completely destroys the topological properties. And so, there we go. We wanted to know, in this case, if scattering SNOM techniques would be able to determine these carrier heterogeneities that weren't detectable with other methods. And so here's a TEM image of some of the bismuth selenide crystals. And here's an image of a nano-imaging image of two of these particular crystals. There's a topography on the top and the nano image on the bottom. And you can see there's some really interesting patterns here. You get a bright outer ring, a dark inner ring, and a bright core. And that happens for both of these crystal shapes. It doesn't seem to matter what the shape is. And so I'd like to just point out that the topography on this nanocrystal, this nanoflake, is very, very flat, but we do see something that looks very similar to an interference fringe. And so from this measurement, it wasn't clear immediately what was going on. Are we probing defects? Are we seeing inter and intraband transitions? Is it a Druder response, surface plasmons, or phonon polaritons? We just really weren't sure. And so, continuing to look at the material a little more closely, a larger collection of these flakes on the silicon dioxide substrate, it was determined that, this near-field response that we see here is rotationally symmetric. You get a bright core, but it depends on the thickness. And so in some cases, with certain thicknesses, the core would be dark. And so there's a very strong thickness dependence. Tuning the photon energies a bit, we see that this bright core pattern with the circles, it persists both in the imaging amplitude and the phase. So essentially the reflectivity and the absorption. It doesn't really seem to change. We do move through the SiO2 phonon polariton resonance, and so that's why you get this inversion of the contrast here. But it seems to exist regardless of what the substrate's doing. And so then that led us to think, well, it has been observed 2D materials can couple to substrates and launch phonon polaritons that way. So to check that out, actually etched the silicon substrate and removed the native oxide. And so by doing that, we were able to see that this light and dark pattern, while it's a little challenging to see here, still exists, even without that phonon resonance. So it's not simply an artifact of coupling to the substrate in this case. So this is where the synchrotron infrared nanospectroscopy came in. So this is another topography image here where we scanned, did a hyperspectral line scan across the surface. And you can see even in this integrated image where it's essentially, we call it like a white light image, integrated over all the frequencies we have access to, you still see this pattern of dark and bright circular regions within the crystal. So scanning across, you have the endpoints here, which are on the bare silicon, and you're moving across the material here. And so you see, obviously, there is this surface phonon polariton from the substrate that's present. That's indeed there. It's present whether we're on the 2D material or not. But there's a lot going on here that isn't present in the bare silicon, bare SiO2. And so if we look more closely as a function of the different positions, we can see that the signal exists very far outside of the Reststrahlen band of the silicon dioxide. And so from this, we're able to say, it really is something special with the bismuth selenide. It's not the substrate itself causing this response. So if we look at 3 specific positions on this little crystal, one in the bright spot in the center, one in the darker spot around the edge, and then in the SiO2 substrate, we indeed see very different spectral responses. So there's a general increase in the signal level within the bismuth selenide, but then we also see this position-dependent signal strength here at the end. And so this group was able to actually model this response and fit it very well simply by varying the local carrier concentration. Very, very small carrier concentrations will actually reproduce these results. And so this was kind of a nice example that this technique is sensitive to very minute carrier density variations that aren't always evident in other techniques. And so the final example that I'm going to present today is on the alpha phase of molybdenum trioxide. And so it's just looking at anisotropy through phonon polaritons in this material. So this particular group was really interested in growing very high quality MOO3 materials. They wanted to make really good Fabry-Perot resonators. And so by varying some of the growth parameters, they were able to get different aspect ratios. And so here's some near-field characterization of some of the different shapes they got. So they had microplates, and they had different aspect ratios of nanoribbons. And so you can see, they did some very nice fitting of the phonon polariton wave vectors in here, and they were able to estimate integer mode orders. And then also comparing to different substrates, they had a nice figure of merit showing that for an ultra-smooth gold substrate, they get minimal loss and significantly enhanced mode compression compared to SiO2. But to really probe the material's anisotropy, they brought the system to the ALS and wanted to probe the 4 different Reststrahlen bands of the material. And so if we measured in the 001 direction of a crystal, and we were able to access the Reststrahlen bands in the Z1, the X, and the Z2 direction. And then probing in the other direction, 100, we can again see signal in the Z1, the B, and the Z2 directions. And so this just demonstrates with some very nice hyperspectral images that you can see multiple Fabry-Perot resonances. The anisotropy in this material is very well defined. And so by taking cross-sections of these different modes, you can actually quantify how good the materials are. And so you can get mode orders, Fabry-Perot resonances, up to 10 in this direction. In the Y direction, it actually goes up to 5. And then likewise, you can see in the 2 Z directions, there are also some very nice mode profiles. Further, if we do a Fourier transform of these 2 regions here, the X and the Y in the 2 different directions, we can actually experimentally recover the hyperbolic phonon polariton dispersion, which is a very nice representative example of the power of this technique. And so I just want to end here. So this is light matter coupling with synchrotron infrared nanospectroscopy. It's a really good probe of anisotropy in 2D materials. So we have some additional capabilities that I didn't necessarily highlight today. So our talk on Monday talked about different AFM modalities, and so we've incorporated some of those into our standard near-field spectroscopy end stations. So surface potential or KPFM mode, conductive and magnetic force microscopy are all available. And this is all free if you have a successful user proposal. I mean, you have to travel to get to the ALS, but I think it's worth it. This is the view from the lab. If you have any questions and you don't have time to chat with me today, we have a little infrared site here where we have a lot of our information about our capabilities, which I've only briefly mentioned. And then I'd also like to point out that we are hiring. The ALS is expanding greatly. So if you have a postdoc or a soon-to-finish graduate student who might be interested in doing measurements at the ALS full-time and helping users and getting to experience a wide variety of science every day, then please point them in this direction. So I'd be happy to take questions at this point.
Thank you very much, Stephanie, for this beautiful overview of the capabilities that you can do at a synchrotron light source. And also thank you for staying exactly in time. We have a question.
Yes, thank you indeed for the nice talk. Well, talking about the strain, do you have a possibility to apply controllable strain to your samples?
We are in the process of developing something. So we have some collaborators at the ALS who've developed some piezoelectric devices where you can apply dynamic strain while taking measurements. And we're trying to get them into a geometry that's compatible with our AFM system. So very, very soon. I would say in the next 6 months we'll have something. So we'll be able to apply at least compression, but ideally tension as well, in plane.
Mm-hmm. Next question in the back.
Okay, thank you for your nice talk. And I have a little question, a little bit off from your topic.
Okay.
But at the very front of the presentation, the formation of the BN growth, like dome shaping growth, that concept is very new to me. And is it already widespread and well known by the community, or?
I'm sorry, could you repeat the end of that? You said it's new to you, and then what?
Yeah, that concept of forming of the BN layer,
yes.
is it very widespread, or any some your hypothesis, or?
Yeah, I would say so. I'm not incredibly familiar with the world of HBN growth and processing. That's a very good question, and I'll say the supplemental material for that paper, and I can talk to you about it afterwards, has a lot of information on how exactly they did those calculations and how they came up with the theory of the way the dome collapsed. And so I'd be happy to talk to you more about that, but I wasn't personally involved in the sample processing. So.